Hello everyone and welcome to Euclid Book 1 Proposition 13. So this is another argument or proof proposition, and so your picture doesn't matter as much as long as it's decent enough to follow along with. And then on the right hand side here I've sort of translated Euclid's argument into semi-modern notation anyway to help us follow along. And now I'll just go ahead and roll through it. So Euclid says if a straight line set up on a straight line make angles, it will make either two right angles or angles equal to two right angles. Then he says, for let any straight line AB set up on the straight line CD make the angles CBA and ABD. So the two straight lines we're caring about here are AB and CD. Those are sort of our original straight lines. And the angles we care about are CBA, which is this angle right here, and ABD, which is this angle right here. So those are the two angles we care about. And then Euclid says, I say that the angles CBA and ABD are either two right angles or equal to two right angles. So in other words, each of these angles is 90 degrees, or the sum of them is 180 degrees in modern speak. Okay. And Euclid continues. Now, if the angle CBA is equal to the angle ABD, they are two right angles immediately by Book 1, Definition 10. So if this angle equals this angle, then by Definition 10, you have two equal angles set up on a straight line, which means automatically and immediately they are two right angles, and we're done. Okay? Bada boom. We're done. But the more interesting case, of course, is as shown in this picture when this angle is not equal to this angle. And what do you do then? So Euclid continues. But if not, let BE be drawn from the point B at right angles to CD. So if not, draw line BE here from point B that is perpendicular to CD. We can do that by Proposition 11, okay, which we just did recently. And then it says, therefore, the angle CBE and EBD are two right angles. So if you do that, then of course, this angle right here is a right angle. Ooh, there we go. And this angle right here is a right angle if you've drawn this line perpendicular to this line, okay? And so I've begun translating his notation then. So if you do that, then CBE equals EBD, and they are both right angles. Which, of course, would also mean that the sum of them is equal to two right angles, of course, okay? So Euclid continues. Yes, so therefore the angles CBE and EBD are two right angles. Then, since the angle CBE is equal to the two angles CBA and ABE, so he notes that CBE right here, this angle right here, is equal to this angle right here, CBA, plus this angle right here, ABE. So I've noted that here. Well, CBE is equal to CBA plus ABE. Okay, there we go. And then he says, well, if that's true, then let the angle EBD be added to each. Therefore, the angles CBE and EBD are equal to the three angles CBA, ABE, and EBD. So in other words, in modern notation, if this is true here, CBA equals CBA plus ABE, then we can add what is really the angle on the other side here, EBD right there, to both. So then CBE plus EBD would be equal to CBA plus ABE plus EBD. There we go. Okay, this should make a lot of sense. Now I'm going to get rid of all these angles. That's the first part of the argument. Second part of the argument. Is, again, since the angle DBA is equal to the angles DBE and EBA, so then he looks at this angle right here, DBA, right there, and notes that it is equal to DBE and EBA, which is this angle plus this angle, which of course is correct, okay? So I've written that also, hey, DBA is equal to DBE plus EBA. There we go. Then he continues, so in that case, let the angle ABC be added to each. Therefore, the angles DBA and ABC are equal to the three angles DBE, EBA, and ABC. So we say, hey, if this is true, then we could add angle ABC, which is actually this angle right here, to both. So then DBA plus ABC would be equal to DBE plus EBA plus ABC. Okay, there we go. Then he says, but the angles CBE and EBD were also proved equal to the same three angles, and things which are equal to the same thing are also equal to each other. In other words, let me back this up here. You should notice that this right side right here and this right side right here are actually the same thing. So it looks a little different, but CBA and ABC are the same angle, right? So this thing right here is also this thing right here. DBE and EBD are the same angle. They're both this angle on the left. So this angle is this angle. And ABE and EBA are also the same angle. That's a little angle in the middle here. Okay, so this is also this. So therefore, this right-hand side and this right-hand side are the same, which means that, hey, so if this equals to this, then this must also equal this. By common notion 2, things which are equal to the same thing are also equal to each other. So then we can say, since those final two are the same, that, hey, DBE plus EBA plus ABC is equal to CBE plus EBD, the left-hand side up here. But we know that this is two right angles, okay? And then the final part of the proof is to note that DBE plus EBA right here, those two, is in fact dBA. This and then that is the second of the two angles, of course, and we are done with the proof. So just to finish that out, Euclid says, but the angles CBE and EBD are also proved equal to the same three angles, and things which are equal to the same thing are also equal to each other by common notion 1. Therefore, the angles CBE and EBD are also equal to the angles DBA and ABC, but the angles CBE and EBD are two right angles. Therefore, the angles DBA and ABC are also equal to two right angles. Therefore, etc. QED.